Hello and welcome to this GeoStudio Tech Talk. Today's webinar will focus on interrogating seepage results and dealing with convergence issues. I'm Vincent Castonguay. I work as a research engineer with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 60 minutes long. Attendees can ask questions using the chat feature. I'll make sure to respond to these questions via emails as quickly as possible. And a recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields. Today's webinar relates specifically to SEEPW, but the content will also be applicable to SEEP 3D as well. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoStudio website. There you can find tutorial videos, examples with detailed explanation, and engineering books on each product. Have you ever performed a seepage analysis in SEEPW and been met with results view where the pore water pressure contours and piezometric surface location were obstructed by a cluster of red X's and gray O's? You might have been wondering what was going on, or your engineering instincts might have already alerted you that something weird was going on with your seepage simulation. This might have been your first experience with numerical convergence, an important topic of numerical simulations. One that is important to consider and understand, but one that many SEEPW users also dread because of how complex it seems at first glance. Well, dread no more. Today is the day we dive into convergence issues in SEEPW, so we can understand together how to go from this little monstrosity to this well-behaved seepage analysis, where convergence is no longer an issue, and where we can confidently trust our simulation results. This webinar will revolve around convergence in SEEPW and how to interrogate the software to understand our numerical simulation results. We will demonstrate what is convergence and why it is such an important aspect to consider to obtain accurate numerical modeling results in SEEPW. To help us along the way, we will be using a practical example of a tailings dam where convergence was initially difficult. I will demonstrate how to properly understand what the convergence issues are in this example and how to solve them. As some of you may already have experienced in the past, tailings dams are great practical examples to study convergence issues because they often provide a high level of complexity, which makes them prone to convergence issues. They generally include many materials where high hydraulic conductivity contrast will exist, and they often include a large number of finite elements. The tailings dam we will be focusing on today is a geometry I made up for the demonstration. The orange material is the tailings deposit, and the two bottom layers are natural deposits. The dam is constructed from the three upper layers, as well as the thin low permeability green layer. The specific properties of each layer won't be presented, as my goal in constructing this model was to create a situation where convergence was difficult. There are three types of boundary conditions used. On the upstream side of the dam, a total head boundary condition is used to simulate the measured elevation of the water table. Having the boundary condition applied to the top of the tailings deposit instead of the far-field left side edge of the geometry is a bit unusual. I have chosen to apply it this way to better represent how tailing materials are deposited fully situated on the underlying materials, which decreases the depth of the water table, even very close to the dam. On the downstream face of the dam, a drainage boundary condition is used, with the potential seepage phase review option ticked on. This will allow the solver to calculate where the water should exit the dam based on the hydraulic regime that develops within the dam. Finally, a zero water pressure boundary condition is used at the toe of the dam to represent a known discharge zone along the ground surface downstream of the dam. With these boundary conditions in place, and given how the light blue material deposit has a low hydraulic conductivity, we expect a water flow regime to develop within the dam where water should exit the dam through the brown material. Finally, let us take a quick look at the meshing I designed for this model. The meshing is coarser towards the bottom of the model, as it is expected this portion of the geometry will remain fully saturated. The dam is modeled using smaller finite elements to ease calculations where saturated, unsaturated behavior might develop. Whenever I take on the task of simulating seepage through a dam or any similar structure, I like to use a two-step approach. The first step consists of a simplified approach to seepage modeling, where we pose the hypothesis that all soils will remain fully saturated once steady-state seepage conditions are reached. The idea of this first step is to help identify where to put our focus on step 2, where we will develop saturated, unsaturated hydraulic properties where needed. The two sub-steps included in step 1 are, first, to attribute a representative saturated hydraulic conductivity to all materials used in the models. And secondly, to review the simulation results and identify each material where our fully saturated flow hypothesis doesn't hold true. The second step to this approach will be to build on the information gathered in step 1 and properly simulate the saturated, unsaturated flow that will develop in certain areas of the model. The two sub-steps for these are to define saturated, unsaturated material models where unsaturated flow occurs based on the observations from step 1. And secondly, to review the simulation results with these new material models and repeat step 2a if necessary. Accounting for unsaturated flow might greatly affect the simulation results, and so materials that were previously expected to remain fully saturated could now show unsaturated flow, and must thus also be modified to account for this. Let us apply this two-step approach to simulate seepage through our tailings dam. At first, I will define all material models as fully saturated. To do this in GeoStudio, all I need to do is choose the saturated only material model and define a representative saturated horizontal hydraulic conductivity, as well as a saturated volumetric water content for each material. Once this is done, I can solve the analysis and review the simulation results. Using contour plots in the results view, I can assess my simulation results. Plotting contours of pore water pressure, I can see the pore water pressure distribution in the dam. Notably, I notice the zero water pressure contour line develops within the dam with negative pore water pressure above it. This indicates suction develops in some areas of the dam. To better understand these results, let me draw a zero water pressure isosurface. This function will draw a surface or a line when the analysis is in 2 dimensions, linking together all the points where the pore water pressure is zero, essentially drawing the position of the piezometric surface. Let me now turn off the contour lines. Viewing the material colors in conjunction with the position of the piezometric surface allows me to identify the materials where unsaturated flow develops. In this case, the orange, green, red, and blue materials are all crossed by the piezometric line. The material portions that lie above the piezometric line have negative pore water pressure, where unsaturated flow will occur. Based on this two-step approach I laid out a moment ago, these materials should be simulated using a saturated-unsaturated material model. A valid question one might have is, what is the fundamental issue with simulating water seepage with only saturated material models? Well, to answer this question, let me plot the flow rate through the center line of the dam. In Results view, I click on Graph and add a new plot. I choose the water flow type and water rate subtype, which I will plot against the Y coordinate. I now need to pick a location from where to draw the data for the plot. I choose the subdomain cross-section option, which allows me to simply draw a line through the domain. The software will automatically select a section of the subdomain and query points closest to the line I draw. Back to the plot, I would prefer to view this plot with the y-coordinate on the y-axis. I can do this by right-clicking anywhere on the plot and choosing Options. I can finally tick the Rotation 90-degree box. This plot now shows how the water rate, or seepage quantity in other words, varies within the body of the dam. Remember, I can right-click on any plot to copy its data if I want to bring the data into another software like Excel, for example. This is what I have done here. I have plotted the position of the phreatic surface. As you can see, the water rate is greater above the phreatic surface than below. This means that there is more water flowing in the dam above the water table than below it. You will agree with me that this doesn't make a lot of sense. It perfectly exemplifies the need for proper saturated-unsaturated soil models in these situations. As we will see in a minute, whenever a soil desaturates, its hydraulic conductivity decreases, which also decreases the amount of water that can flow through it above the phreatic line. Now that we have identified zones and materials where unsaturated flow occurs in step 1, we should switch the appropriate material models from saturated only to saturated-unsaturated in SEEPW. As you can see, this material type requires 2 entries in the form of functions, a volumetric water content function and a hydraulic conductivity function. These functions should ideally be measured in a laboratory for better results, but can also be estimated within SEEPW. Let us review what both functions refer to. Starting with the volumetric water content function, this is a plot of the volumetric water content on the y-axis and the matrix suction, or negative pore water pressure if you will, on the x-axis. In the laboratory, we would prepare a fully saturated soil sample and apply increasing suction to slowly desaturate the sample and monitor its volumetric water content through the process. We use a Tempe cell in the laboratory to perform this test. The left side of the plot represents the fully saturated conditions towards the lowest suction values. In this case, the saturated volumetric water content is 39%, meaning that at saturation, 39% of the soil's volume is occupied by water. As matrix suction increases, the soil initially remains saturated, up to a point called the air entry pressure, where the saturation will begin. As matrix suction continues to increase, the saturation will process. At high suction values, the volumetric water content will tend toward the residual volumetric water content, which is not zero in the vast majority of cases, meaning there will always remain some quantity of water trapped in the soil's pores, even when a very large suction exists. The volumetric water content function should be defined in SEEPW when a saturated-unsaturated soil model is used and a theoretical capillary model is used to estimate the hydraulic conductivity. If the hydraulic conductivity function is manually defined, and whenever a transient seepage analysis is performed, the volumetric water content function must imperatively be defined. The second function needed to complete the model definition is the hydraulic conductivity function. While we measure the volumetric water content function through the desaturation process, we also measure the speed at which water is drawn out of the sample. Similarly then, the saturated hydraulic conductivity is located to the left side of the plot at the lowest matrix suction values. As suction increases and the air entry pressure is eventually reached, the saturation begins and the hydraulic conductivity starts to decrease. As more air replaces water in the soil's pore, water transfers get increasingly difficult. The saturated hydraulic conductivity thus corresponds to the highest hydraulic conductivity a soil can exhibit. The hydraulic conductivity function must be defined in SEEPW to complete the definition of a saturated-unsaturated soil model. When resolving a seepage analysis in SEEPW in which saturated-unsaturated material models are used, a problem inevitably arises. Some of you who are keen observers might already have spotted the issue. When resolving the finite element equations, we want to calculate what the pore water pressure is at every point in the domain. To achieve this, we first need to know the volumetric water content and hydraulic conductivity at every point in the domain. However, referring to the characteristic plots we see here, to get this data we first need to know the pore water pressure. So it seems we must know one to know the other, but we must know the other to know one. Clearly, hypotheses will need to be made to get us going. Note that in steady-state seepage analyses, the volumetric water content function is not used by the solver because water content cannot vary, as opposed to a transient analysis. To resolve this double unknown situation, the solver will pose a trial matrix suction, which it will use to then calculate the corresponding volumetric water content and hydraulic conductivity. With this information in hand, the solver will resolve the finite element equations using the boundary conditions we have imposed in the model and calculate the pore water pressure at every point in the domain. Once this first trial is done, the solver will return back to the initial trial matrix suction it has posed and verify if the calculated pore water pressure matches with the hypothesis. Chances are both values won't be the same. The solver will then correct the pore water pressure value and recalculate the volumetric water content and hydraulic conductivity, and use these new values to solve once again the finite element equations in search of the pore water pressure in the domain. Once again, once the pore water pressure is calculated everywhere in the domain, the resulting values are compared to the hypotheses. If both are not the same within a certain tolerance, the solver once again uses the new values to calculate the volumetric water content and hydraulic conductivity and starts the process over again. This iterative process will go on as long as the pore water pressure used on a given iteration doesn't match with the calculated values from the following iteration. In most cases, the solver needs a few trials and will succeed in finding a converged solution. However, if the model contains several saturated-unsaturated material models, or if some of the functions used are very steep, meaning that a small change in matrix suction can lead to a large change in corresponding hydraulic conductivity value, finding a proper converged solution might prove difficult. This is in essence the issue we will be tackling together in this webinar. Coming back to the simulation results from our tailings dam analysis that used saturated-only material models, we had identified the materials that we should model using saturated-unsaturated material models to accurately simulate their associated unsaturated zones. Let me do this for the granular layer of the dam structure. In GeoStudio, when going into Define Materials, I can clone any material and change its material model. I can define the volumetric water content function, which will be used to estimate the hydraulic conductivity function by clicking on the ellipsis. Starting with the volumetric water content function, I click on the three dots to create a new function. There are three main types of functions I could create: data point, Verdelunxing, and Van Genuchten. The last two options are parametric models used to represent the volumetric water content curve. They both require a set of input parameters to generate the curve. I will instead use the first option and estimate the function with SEEPW's sample functions, using the sample sand material. I am required to input the saturated volumetric water content to generate the curve. Note that if you had access to laboratory measurements, you could instead copy-paste the data points instead of using the estimated functions. Similarly, for the hydraulic conductivity function, I will estimate the curve with a theoretical capillary model. We have two models available to generate the function: the Verdelunxing-Huang model and the Van Genuchten model. I will use the latter here and select the previously created volumetric water content function for this material as an input. The saturated hydraulic conductivity and residual volumetric water content are required to generate the curve here. Once both of my functions are defined, I can choose them to complete the definition of my saturated-unsaturated material. I should repeat this process for each material that I have identified in the first step of my modeling process wherever unsaturated flow occurs. For our tailing dam, we obtain these pore water pressure conditions in the domain once saturated-unsaturated models are used. For comparison with the previous solution where saturated-only models were used everywhere, we used to obtain this solution. As you can see, the pore water pressure distribution is quite different, especially in the dam's central portion, where the piezometric surface is now located lower down, creating a larger unsaturated zone in the dam. However, this pore water pressure distribution might not paint the full story. As we discussed a moment ago, using saturated-unsaturated material models will now require that the solver iterates to find a properly converged solution. By going into the View Preferences window, we can turn on Node Convergence to view if we had any convergence issues once the analysis was resolved. With Convergence activated, the analysis now shows an abundance of gray O's and red X's. Let us look closer at these and what they mean. At first glance, you would think that this is just the SEEPW solver playing a game of tic-tac-toe with your analysis. But no, these symbols refer to the convergence criteria used in SEEPW. You can find these criteria in the Water tab on the Define Project window. There are two convergence criteria in SEEPW: the maximum pressure head difference, to which the gray O's relate, and the significant digits equal, to which the red X's relate. Let us look at both more closely. The maximum pressure head criterion ensures the pressure head value at a given node does not vary by more than a chosen tolerance between the last two iterations of the solving process. This convergence criterion is thus verifying the numerical stability of the solution for small pressure differences. By default, this tolerance is set to 0.005 meters when a new SEEPW analysis is created. Let us consider an example with digits to fully understand how this tolerance is checked. On the first to last iteration, the pressure head value is 23.5645 meter at a given node. This pressure head value changes to 23.5585 meter on the final iteration. The pressure head difference between these two iterations is 0.06 meter. This is larger than the allowable tolerance, which is 0.005 meter. To highlight the failure to comply with the allowable tolerance on that node, SEEPW will display a gray O in results view. For any node where the maximum pressure head difference criterion fails, the solver will check a second convergence criterion to verify if the convergence issue is very important: the significant digits equal criterion. While the first criterion checks for numerical stability for small pressure differences, the second criterion investigates if the answer remains the same from one iteration to the other when larger pressure differences are involved. This tolerance is set to 2 significant digits on the pressure head value by default. In other words, if 2 pressure head values are expressed with 2 significant digits, they should be exactly the same for the tolerance test to pass. Using our test values that failed the first convergence criterion, if we express both using only 2 significant digits, they both take a value of 23 meter of pressure head. Since there is no pressure head difference between these two values once expressed with 2 significant digits, they passed the second convergence criterion. A gray O would still be displayed on the analysis results to indicate that this node failed the first convergence criterion. Let me now tweak our test values just a little bit by changing the pressure head from the first to last iteration to 24.5645 meters. Comparing the values between these two iterations will still fail the first convergence criterion, so the second criterion will be checked. This time, expressing both values with two significant digits will yield a pressure head difference. And since the second convergence criterion now fails, a red X will be displayed at this node in the analysis results instead of a gray O. As you can see, a red X indicates a worse convergence issue than a gray O. While gray O's normally indicate light convergence instability between iterations, red X's really require your attention as they indicate the answer is changing profoundly between iterations. Coming back to the results from our tailings dam analysis, we undoubtedly have important convergence issues that need to be resolved before we can accept the results of our analysis. The rest of this webinar will focus on how to remediate bad convergence using the tools available in SEEPW. Let us now get back into GeoStudio to see what we can do about our convergence issue. In this file, I have prepared some analyses to get us from bad convergence results to good convergence results. The two geometries available in the Project Explorer are identical. I created a second geometry for the sole purpose of clearly separating the major analysis results, geometry A, and the path from bad to good convergence in geometry B. Whenever you conduct a SEEPW analysis and see convergence indicators, the gray O's and red X's, in your simulation results, the first thing I would advise you do is to open the graphing tool and prepare the following two plots that display convergence. Firstly, the hydraulic conductivity plot will show what the input hydraulic conductivity function was for the materials used in the analysis. These will be the solid markers. And we'll compare these to the hydraulic conductivity values the solver ended up using. These are the hollow markers. When convergence is good, both series are right on top of each other for each material, meaning that the hydraulic conductivity values used by the solver match the input function used, just as we see on this plot. However, when convergence is bad, both series will diverge, giving us a clear indication that our solution is wrong. This plot is normally already defined by default when you solve a SEEPW analysis. The second plot we should be looking at to diagnose and resolve convergence issues is the unconverged pressure head nodes versus iteration number plot. This plot can be created from the convergence each iteration kind. The plot displays how many nodes from the analysis are unconverged at each iteration. If we were to stop the solver at any point, the number of nodes where a red X would be displayed would be equal to the value displayed in this plot. When convergence is good, the plot looks like there is order to it, with patterns repeating. But when convergence is tough, the plot might just look like a bunch of points. To properly understand what this all means, let me plot this again in Excel with a bit more colors. On this plot, I have attributed a specific color to each of the boundary condition reviews the solver went through in order to find a properly converged solution. I'll explain in a minute what a review is, but let me first zoom in to the beginning of this plot. We now only see the first few hundred iterations of the solving process. The blue line is the initial trial the solver did. The red line is the first review, and the gray line is the second review. On this plot, we immediately notice the various lengths of the segments. The blue and red curves are short, meaning they don't comprise many iterations, while the gray line is lengthy, it ran for many more iterations. There are two reasons why a review would stop and thus be shorter than another review. The first reason is what we desire. Convergence has been reached. No need to iterate anymore. This is what happened for the blue and red curves. They both reached a point where there were no more unconverged pressure head nodes. To clearly indicate whenever a review reached this state, I've inserted a red dot at the end of a converged review. The second reason why a review would stop is not as pleasant. The maximum number of allowed iterations was reached before there were no more unconverged nodes, so the process had to stop. In the case of the second review, the gray curve, after 500 iterations, the review stopped. This is the default maximum number of allowed iterations in SEEPW. I've mentioned the word review a few times already, but what are these? To understand this, let us go back to GeoStudio and take a look at what the solution looks like after the first review. Keep in mind, as we see on the plot here, there are no unconverged pressure head nodes anymore after the first review, which means the solution has converged. Let us see what it looks like at this stage. Here is what the pore water pressure distribution looks like after the first review. As we can see, no convergence symbols are being displayed, confirming that proper convergence was achieved. If we take a look at our two convergence plots, we see that all the hydraulic conductivity functions were well respected by the solver, and the unconverged pressure head nodes correctly indicate 0 at the end of the review. So all seems well. However, the clever geotechnical engineers that we are will rapidly spot that weird-looking phreatic surface near the downstream portion of the dam. The phreatic surface seems to be climbing upward as it prepares to exit the dam, which is very suspicious to say the least. If I display the boundary conditions used in the analysis, we will recall that the drainage boundary condition was used on the entirety of the downstream face of the dam. In the defined boundary condition window, I can see what a drainage boundary condition effectively is. There are two components to this boundary condition. First, it is a zero water rate boundary condition. Implicitly, the entire perimeter of the domain in a SEEPW analysis comprises a zero water rate boundary condition, so that water can only enter or exit the domain, where we specify so via another boundary condition, like the total head or zero pressure boundary condition we have applied elsewhere in the domain. It is thus the second component of the drainage boundary condition that specifically makes it a drainage boundary condition. The potential seepage phase review option is ticked on at the bottom of the window. This option will allow the solver to switch individual nodes where the boundary condition is applied to either a zero water rate or a zero water pressure boundary condition. It is up to the solver to decide which nodes should use one type or the other. When the zero water pressure type is applied, pore water pressure is not allowed to build up and water must exit the domain. A priori, the solver doesn't know which nodes on the potential drainage surface should have the zero water rate type of boundary condition and which nodes should have the zero water pressure type. In other words, when the solver starts, it doesn't know where the phreatic surface should exit the dam. So it initially assumes all nodes have the zero water rate type. It solves the analysis and examines the solution to determine if it is proper. If it is not, then it will turn water seepage off at some nodes and allow water out through the zero water pressure boundary condition type. It will solve the finite element equations again and repeat the examination process. This procedure is what the reviews I mentioned earlier are. Each time the solver concludes the solution is not proper with regards to the drainage boundary condition, it must make another review where it tweaks the solution. It will make new reviews as long as there are nodes on the drainage boundary condition that needs adjustment. So how can a solution be proper or improper with regards to the drainage boundary condition? As we know, the drainage boundary condition can control both the water rate and the water pressure where it is applied. Let us then plot both of these values on the downstream face of the dam with respect to the y coordinate. By holding Ctrl on my keyboard, I can select both plots, right-click anywhere on the combined plot, and choose Copy Graph Data so that I can plot this again in Excel to have a different perspective on the data. The water rate is plotted in blue here, and the pore water pressure is plotted in red. This plot can be divided into two zones. In the upper part, the water rate remains at 0, while the pore water pressure is allowed to vary. This means this upper part of the dam's downstream face has the 0 rate boundary condition type. In the lower part, we see the inverse. The pore water pressure remains at 0 and the water rate is allowed to vary. In other words, in this review, the solver allowed the water to exit the dam at an elevation of 54 meters by allowing the water rate to be non-zero. And indeed, if I overlay the dam's section on top of this plot, we can see how the dashed blue line representing the piezometric surface exits the dam where we identified the change in boundary condition type chosen by the drainage boundary condition. If we take a closer look at the water rate values reported here, you might notice something odd. At the bottom, the water rate is negative, meaning that water is coming out of the domain as expected. However, notice in the upper portion, the water rate is positive. To respect the boundary condition, the solver had to inject water into the domain so that pore water pressures at the drainage surface would be 0 and the boundary condition definition would be respected. This is of course problematic. Water can come out of the dam on the drainage face, but there is no way it should come in unless an infiltration flux is simultaneously applied, which is not the case here. Once the analysis is solved, the solver will identify the solution as wrong because of this water intake, which will trigger another review to happen. On the following review, the nodes where water had to come into the domain will be switched to the 0 rate boundary condition type instead of 0 water pressure, and the solver will solve the finite element equations once again. At the end of the review, the solver will once more verify if the solution is proper. If there are no more nodes where water comes into the domain, the solver will stop the process and the final solution will be displayed. If there are still problematic nodes, another review will be triggered. This process will go on until a proper solution is found, or until the maximum number of reviews allowed for the analysis is reached. By default, 10 reviews are allowed, but as we will see, this is a user-defined value we can alter if needed. Now that we know what reviews are, let us take a look back at our unconverged pressure head nodes plot from our initial analysis. As we can see in the legend to the right, the solver performed 10 reviews in this case, which is the maximum number of reviews it was allowed to perform. There is thus a chance the solver might have needed a few more reviews to arrive to a proper solution. If we plot the water rate and pore water pressure profiles as we did earlier, we can see that the water is still entering the domain through a few nodes, so at least another review would have been needed here. We can adjust the maximum number of reviews allowed in a given analysis in the Define Project window in the Water tab. The Convergence settings for the analysis are all conveniently located here. The maximum number of reviews can be changed, and I will increase it to 15 here. Also, note that the two convergence criteria responsible for the display of gray O's and red X's can be adjusted here if needed, which should be assessed on a project-to-project basis. Once the maximum number of reviews allowed is increased from 10 to 15, The unconverged pressure head nodes plot still shows that the maximum number of allowed reviews is reached. However, this isn't very surprising. The convergence plot shows every review, starting from the fifth one, was stopped because the maximum number of iterations allowed was reached. In other words, when the solver was reviewing the results at the drainage boundary condition to assess if it needed to switch some nodes from zero water rate type to the zero water pressure type, it was using an unconverged solution, which is sure to pollute the drainage boundary condition assessment. Upon seeing those results, one could wonder if increasing the maximum number of iterations allowed couldn't solve the convergence issues we are facing. Especially, see how the number of unconverged pressure head nodes was going down steadily during the fifth iteration. If more iterations had been allowed, maybe the solver could have converged on this review and a proper solution could eventually have been reached. Going back to GeoStudio, in the Define Project window, I can increase the number of iterations the solver is allowed to perform for each review here. Let us increase this number from the default 500 to 1000. Once the solver has finished solving the analysis, a quick look at the results shows how convergence was undoubtedly still not achieved. The convergence plot for this analysis shows how convergence was now reached for reviews 5 and 6, which wasn't the case previously. However, we see in the legend that the maximum of 10 reviews was still reached, so there is a chance the solver might have needed to perform some more reviews to provide a proper solution. Plotting the water rate and pore water pressure profiles on the downstream side of the dam, where the drainage boundary condition is applied, sure does show that water is still coming into the dam, so the solution is still wrong. By increasing the number of reviews allowed from 10 to 15 when 1000 iterations are also allowed, now shows that 2 more reviews were used by the solver before it finally stopped on review 12. At this point, the drainage boundary condition is perfectly respected at every node located on the downstream face of the dam, and the solution is proper. However, obtaining a proper solution in the sense that boundary conditions are properly respected doesn't mean that the solution is good. Taking a look at our results, the entire analysis is still plastered with bad convergence symbols, and the phreatic surface seems to be going on quite a roller coaster. Clearly, the solution the solver arrived at is not the solution we are looking for, one where boundary conditions are respected and where both convergence criteria are met at every node in the domain. Looking back at the convergence plot, we can spot patterns of what looks like repeated solutions being tried by the solver. Notice how, after an initial downward trend in unconverged nodes, the solver fails to maintain the downward trajectory and instead begins to oscillate. Let me isolate review number 10 to get a clearer picture of the phenomenon. Initially, the solver was making good progress in trying out new solutions that resulted in fewer nodes being unconverged. However, after a few hundred iterations, the solver seems to have run out of ideas on how to decrease the number of unconverged pressure head nodes, and things seems to mostly remain the same for the remainder of the iterations done. If I highlight a few sequences here, we can see how this pattern is being repeated almost identically as the number of iterations climb up. This indicates the solver is stuck in a repeated substitution loop which won't provide any better results even with large number of iterations being allowed. High nonlinearity in the hydraulic conductivity functions used for the various materials in the domain is causing this convergence issue. The solver should be allowed to try out smaller solution change increments to account for the large nonlinearity of the material models. This is where altering the under-relaxation criteria can do wonders. These criteria are located with the other convergence parameters on the Water tab of the Define Project window. There are 4 variables we can control to adjust under-relaxation in SEEPW, all of which are related to a single variable, alpha. Alpha is the rate of relaxation which will control the progression of the solution and reduce the propensity for oscillation. In this equation, the unknown is the under-relaxed pore water pressure U at iteration n. The newly calculated pore water pressure for the current iteration is influenced by the pore water pressure from the previous iteration. The rate of relaxation, alpha, will dictate how much the pore water pressure from the previous iteration will influence the current pore water pressure. In the case of repeated substitution, when alpha is set equal to 1, the current pore water pressure is exactly equal to the tentative pore water pressure. In other words, there is no influence from the previous iteration. However, if alpha is smaller than 1, say 0.65, the pore water pressure will be composed of 65% of the tentative pore water pressure and 35% of the previous pore water pressure. As you can see, depending on the value of alpha, the solver will move on more or less rapidly from the solution of the previous step towards a new solution. When alpha is small, the changes are smaller from one iteration to the next, which is important when non-linearity is very large in the input material model functions. As we saw in GeoStudio a moment ago, there are 4 variables we can control to affect the under-relaxation scheme. The initial rate will define the initial value of alpha. By default, this value is set at 1, meaning that the under-relaxation scheme is initially turned off. However, after a set number of iterations, alpha will be multiplied by a rate reduction factor to reduce its value in order to reduce the changes from iteration to iteration. The default rate reduction factor is 0.65. The reduction frequency will determine how many iterations need to conclude before alpha is affected by the rate reduction factor. This value is set at 10 iterations by default. Finally, the minimum rate is the smallest value alpha can take, which is 0.1 by default. Whenever convergence is difficult in SEEPW analyses, we often make the following adjustments to the under-relaxation parameters, which we call the golden numbers, because of how effective these changes often are to reach a properly converged solution. The initial rate is set to 0.65 instead of the standard value of 1, so that the under-relaxation scheme comes into effect right at the onset of the iteration process. The minimum rate is also decreased to 0.01 instead of the default value of 0.1, so that smaller alpha values can also be trialed. These simple adjustments can generally do wonders when convergence is difficult. Let me return to GeoStudio to see if applying these golden numbers to our tailing dam analysis can help us achieve good results. Back in GeoStudio, I applied the golden numbers to the under-relaxation criteria for this analysis. As you can see, the initial rate is now set to 0.65 and the minimum rate is set to 0.01. Looking at the solved result for this analysis immediately shows very promising results. The number of bad convergence symbols overlaid on the results is very noticeably smaller than the results we previously had. But still, we do see some convergence issues. Looking at the convergence plot, we see how different it looks now that we have allowed the solver to proceed in a more controlled manner by altering the under-relaxation parameters. Every review proceeds with a downward trend toward lower numbers of unconverged pressure head nodes. It seems, however, that more iterations would be needed for most of the reviews to achieve a converged state. For example, notice how the 5th review almost got to 0 unconverged pressure head nodes but was stopped in its tracks because it had reached 500 iterations, the maximum allowed by default. By simply increasing the maximum number of iterations allowed to 1000, every review now reaches proper convergence. However, we reached 10 reviews, the maximum number allowed by all default settings. So it would be wise to allow for a few more reviews, just to make sure the solver wouldn't have needed some more reviews to properly respect the drainage boundary condition at every node on the downstream face of the dam. As we had anticipated, allowing for 15 reviews gave the solver an opportunity for one more review before finally stopping after 11 reviews. Every review ended once convergence was reached, meaning we can now trust the results obtained from the numerical simulation. Taking a look at our results in GeoStudio, there are no more red X's symbols on the analysis. However, there are still some gray O's overlaid on the analysis results. As we had discussed earlier in the presentation, gray O's mean the first convergence check failed at the nodes where they are displayed, meaning there is still a bit of numerical instability in this area of the analysis. A quick and easy way to correct this situation is to force the solver to respect a tighter tolerance when it checks the number of significant digits that are equal at 2 successive iterations. The last analysis from our analysis tree applies this fix by increasing the number of significant digits that must be equal from 2 to 3. As you can see from the solved results, the solution is now free of convergence symbols. The pool water pressure contour lines we see represent the final answer we were looking for, one where proper convergence is achieved everywhere in the domain. We can now have confidence in our results and proceed to use these in our engineering designs and analyses. For completeness of the demonstration, here is what the convergence plot looked like before we made our convergence criteria tighter. And here is what it looks like for the final solution. Each review takes a little bit more iterations to complete since our convergence criterion is slightly more demanding. In the end, we'd end up with converged reviews and a solution where no gray O's are displayed. Finally, taking a look at the hydraulic conductivity convergence plot, we can confirm all our saturated-unsaturated materials properly respect their input functions, which means convergence is good in our analysis as we had confirmed with the previous plots. We are nearing the end of this webinar. To summarize, we saw how crucial monitoring the convergence performance via the unconverged pressure head nodes plot is when it comes to understanding what actions should be taken to mitigate poor convergence. Sometimes, adjusting the convergence parameters is all that is needed. This can include increasing the number of reviews and/or the number of iterations the solver is allowed to make. Some other times, as we just saw today with this tailings dam, adjusting the under-relaxation criteria will also be needed. Using the so-called golden numbers, where we decrease the initial rate from 1 to 0.65 and the minimum rate from 0.1 to 0.01, we can often alleviate the convergence issues. When the materials we use in a simulation include highly nonlinear hydraulic conductivity functions, that is, a function that is very steep, a combination of convergence and under-relaxation adjustments will often be needed to achieve proper solutions. Other convergence mitigation techniques can also be used in tandem with what we discussed today. For example, truncating a material's hydraulic conductive function at values corresponding to vapor conductivity in the order of 10 to the power minus 14 meters per second, refining the finite element mesh in areas where large hydraulic gradients might exist, or using transient analyses to slowly achieve steady-state seepage conditions. These techniques are not required in the vast majority of cases, but it is good to know they exist when the situation is dire. We have now reached the end of this webinar. I hope you have appreciated this in-depth look at convergence and SEEPW. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.